This is the final lecture for Unit 1.1, Electromagnetic Radiation and Atomic Spectra, and we're going to look in a little bit more detail at atomic emission and atomic absorption spectroscopy. By the end of this lecture, you should be able to explain how the absorption lines in an absorption spectrum are produced, and you should also be able to describe how atomic emission and atomic absorption spectroscopy work and how they're used to identify the quantities of elements in a sample. Let's start by looking at atomic emission spectroscopy, which is what we were talking about mainly in the previous lecture. So all that could be summed up by this rather long sentence. So in AES, atomic emission spectroscopy, the sample is energised by heat or electricity, causing electrons to be promoted to a high energy level. Then the wavelength of the radiation emitted as electrons fall back down to lower energy levels is measured. So let's remind ourselves how exactly you would do that again. Okay. So in this picture we're using a flame to energise electrons. Equally it could be passing electricity through the vapour. So the flame energises our electrons to higher excited levels. They de-excite, giving off electromagnetic radiation. And we are interested in the visible region at this stage. So we pass the light through a narrow slit, just get a nice fine beam, pass it through a prism to split it up into its different wavelengths, and then we can detect and measure the wavelengths of the different wavelengths of light that are emitted. And from this we get lots of information about the energy difference between the different electron energy levels within an atom. But we can also use it to find out what atoms are present in a sample, and indeed how much, what is the concentration of the atoms in that sample. Let me explain. Okay, let's okay, say we had an unknown sample and we carried out atomic emission spectroscopy and we measured this spectra showing these wavelengths of light being emitted by our sample. We can then compare that spectra with a library of spectra of known atoms. So for example, beryllium. Okay, our unknown is not beryllium because the wavelengths don't match up. What about copper? Nope, don't match up. Manganese? Nope, don't match up. Strontium? Yes, all the wavelengths that appear in our unknown sample appear in strontium. So we know that there's strontium in our sample. Now, this is it's very important to be able to find out what's in that unknown sample, and astronomers have used this for years to work out what elements are present in stars. So if you collect the light from a star using a telescope, pass it through a prism, split it up into different wavelengths, you can then match those wavelengths to the library of known wavelengths of the elements, and we can work out what elements are present in different stars. So we look at, say, Cirrus, and we'd see that it contains hydrogen and helium, maybe lithium, beryllium, boron, carbon, and that's all. Whereas look at another star, say Betelgeuse, I might find that that's got some heavier elements in it, say nitrogen, oxygen, and indeed this is how helium was first discovered. A scientist was looking at the light coming from our sun, passed it through a prism, got all the wavelengths of light, saw all the wavelengths due to hydrogen, saw the lithium wavelengths, and can match up all the wavelengths from the sun to various known elements, apart from a few wavelengths which didn't match up with any of the elements known on Earth at the time. So the scientists postulated that this was due to presence of a new element, and he called it helium, from the Greek word for the sun, which is helios. Subsequently, helium was found on Earth, the atomic emission spectra measured, and he was proved to be correct. So, very powerful atomic emission spectroscopy. We can use it to identify the presence of elements in a sample, but we can also use it to actually quantify the concentration of the element in the sample by matching the intensity of the light emitted from an unknown sample with samples of known concentration of that element. We can actually match up the concentrations. So the higher the concentration, the more intense the wavelengths of light are going to be. Okay, so the concentration of the elements present is related to the intensity of the light emitted. The higher the concentration, the more intense the light. Right, finally we want to look at atomic absorption spectroscopy, which I always consider to be the ugly sister of atomic emission spectroscopy. They're both very, very, very similar, which makes them quite easy to confuse. In atomic absorption spectroscopy, light is directed at the unknown sample, which absorbs light as electrons are promoted to higher energy levels. So what I'll try and do is contrast the emission spectra with the absorption spectra. So up here we've got an emission spectra. Let's just say this is neon gas. Okay, so we have our hot gas in the emission spectra, so we'd either put it into a flame or passing electricity through it. Electrons are excited, de-excite, give off light. We split it up using a prism and see the different wavelengths of the light emitted. Okay, so that's what we've been talking about. In absorption spectroscopy, the gas is cold. Okay, so we're not using heat to excite the electrons. We're not passing electricity through it, so we're not exciting electrons by passing electricity through it. What we do is we shine white light through the gas, and the gas absorbs some of those wavelengths of light in order to excite the electrons to a higher state. And then if we pass the light that passes through the gas through a prism, we get the spectra going from red to blue, but with a few wavelengths missing, because these wavelengths have been absorbed by the gas. The wavelengths correspond exactly to the wavelengths emitted in the emission spectra, because we're talking about the same energy transitions, just one's going one direction, one's going the other. So we pick this red line here in the emission spectra. Let's just say that's this is the third energy level, this is the fourth energy level. That red light corresponds to an electron falling from the fourth energy level to the third energy level, giving off light of that wavelength there. In the absorption spectra, the sample is absorbing light to promote the electron from the third to the fourth energy level. So light of that wavelength does not pass through the sample, it's been absorbed by the sample. So we just see a missing wavelength in the absorption spectra. Okay, so you get the same information from emission spectra and absorption spectra. You'll be asked more often about emission spectra, but it is important you realise the difference between the two. So basically, in emission spectra, the atoms are emitting the light, whereas in absorption spectra, the atoms are absorbing light, but whether it's emission or absorption, it will do it at the exact same wavelengths. So you should be able to explain now how the absorption lines in an absorption spectrum are produced, and also to describe how atomic emission and atomic absorption spectroscopy work, and how they're used to identify the quantities of elements present in the sample.